Hi, welcome everyone. It's a great pleasure to introduce Dr. Brad Barrett from the U.S. Naval Academy in Annapolis, where they have an oceanography department, where Brad teaches, although he's an atmospheric scientist. And Brad Barrett has a very interesting education and career trajectory that I want to tell you about. He did his bachelor's degree with a double major in business administration and mathematics, and at the University of North Carolina in Chapel Hill. And then he went to graduate school in Norman, Oklahoma, where he studied tropical meteorology, although that school is known for severe storm research, but he worked on tropical storms. And then after his PhD, he worked for a year as a Fulbright Fellow at the Caribbean Institute for Meteorology in Barbados. Then for a year, he was a visiting lecturer at the Wagner Center for Climate at the University of Graz in Austria. And then he was a postdoctoral associate in the Department of Geophysics in University of Chile in Santiago. And then he joined the faculty at the Naval Academy, where he's now an associate professor. And so Brad has done very interesting work in all of these places. He has published several papers relating to the impact of MJO on ozone and particulate pollution in Chile, and climate of Mexico and climate of Chile. And today he's going to tell us about his very bold idea that long-term forecasting is possible for severe storms like tornadoes. So let us welcome Brad Barrett.
Thank you very much. And we'll play with it several times. It's good to be here this afternoon. Thank you for bringing me here to say a few things about some of the work that I had a chance to do at the Naval Academy. I was walking around, it's my first time to Long Island. I was walking on the campus yesterday, and at the Naval Academy, our students are not quite like your undergraduate students here. They're the same age. They're 18 to 22 years old, but they are wearing uniform and oftentimes walking in straight lines and these sorts of things. So it's nice to return to the typical campus life where there's a student union and there's students out sitting in the quad doing student things, whereas our students don't do those things. So that was nice to remind myself of life in Oklahoma, life in North Carolina, yeah, in Chile as well. The Chilean students did the same things. So I was also thinking about the audience here. I think is a mixture of faculty, graduate students, postdocs. I wanted to perhaps give a bit of context to the work on Madden-Julian Oscillation and tornado prediction by way of sort of my own and my students and colleagues' path to arrive at that idea. It was not the very first idea that came to my mind after I had finished my PhD, but I have looked at Madden-Julian Oscillation and its modulation of lots of different facets of the Earth and the atmosphere, and eventually led to the question of, oh, well, if Madden-Julian Oscillation modifies all of these other things, maybe it will also have an effect on severe convection. That idea actually pitched to the National Science Foundation a few years ago, and the reviewers agreed that was something that no one else has ever done and merited a few years of funding. So that's where I've been concentrating my efforts in the last few years in this particular study, but I wanted to give you the lead up to the study. And before that, to be a bit pedagogical for those in the room who may have no interest in climate or are perhaps focusing on coding parameterizations in a mesoscale model or something like that, where you don't have any connection to climate. I thought I would introduce my study a bit by explaining kind of where I got here. We certainly are aware of oscillations. We experience them even if we don't study them. The nice thing about the atmosphere and also the ocean is that whatever you observe is often the superposition of multiple scales of variability, from long term all the way down to the very short term. And there's some nice schematics here that I found online to sort of show this idea. And I'll give an example of possibly something that could perhaps impact the temperature of the atmosphere outside today. That maybe there's some long-term or longer-term variability. La Nina, I think it's neutral phase this very second. Maybe there was a cold front that passed yesterday, for example, or 2 days ago. It's the middle of the day today, so perhaps there's some variability. And the net result of all of these three different modes of oscillation gives you the result that you might observe on a day-to-day basis. And to be a bit more specific about that, I pulled up the Weather Service's climate record of temperatures. I think this is from the MacArthur Airport at Islip. They're calling it Islip area. This is for the year of 2013, so last year. And these blue lines here are the high and low temperature for every single day. The red line is the maximum record temperature ever recorded at that station for the day. And the blue here is the record minimum temperature. So last year you can see that there were some fairly close to being record lows and fairly close to being record highs, and maybe one that was a record high temperature. The faint or behind the scene brown shading is normal temperature. But this is just by way of example that the temperature field for the season, the annual cycle of last year, is the result of superposition. You see the seasonal cycle, it's warmer in the summer and colder in the winter. See that? The daily cycle shows up here with the high and low temperature. Certainly the maximum temperature occurs usually in the day, and the minimum temperature usually occurs in the evening. And what you probably can't see, because this is only a short term 1 year, but there are other longer period oscillations that would project onto this. The Madden-Julian Oscillation would also have some impact, perhaps more so in winter than in summer. But its variability would have to be teased out a bit more than just looking at from our eyesight. We can see the seasonal cycle, but we wouldn't be able to see the shorter term variability. The synoptic variability, some warm periods followed by cold periods, followed by warm periods again as the fronts and wave cyclones pass through. So this is the background of sort of what I've been looking at, and this Madden-Julian Oscillation fits in a nice window that bridges typically weather, which is a forecast on a couple of days to a week or two, and climate, which is more likely 1 month and beyond. A very nice bridge between those two scales of variability. So a bit more about Madden-Julian Oscillation itself, for those who maybe are not that familiar with MJO. It was discovered by a couple of meteorologists who had really miserable careers. They spent years in the tropical Pacific launching radiosondes and doing field project work there. It was a horrible life, I'm sure. So yeah, Paul, Julian, and Roland Madden. Their first signal for what they didn't call it, they called it an intraseasonal oscillation. The community has since named it for them. But the first signal they saw was in surface pressure data confirmed with upper level wind field variability. And they noticed that there was some regular return periods after filtering for fast Fourier transforms or wavelet analysis. They noticed there was some regular return period, 30 to 60 days, and thought that would be interesting. And well, the community has spent the last 40 or 50 years unpacking just how interesting, how key of a component of the Earth system this really is. Andrew Majid, I guess this is his postdoc from New York University, have done some really interesting mathematical decomposition work, and this is just a schematic figure of their understanding of MJO. I really like it because I think it shows that when I talk about MJO phase whatever or amplitude whatever, to really recognize that the summary statements of MJO are kind of this dashed line. That, oh, this will be the amplitude of the MJO here and the one there, but the reality is that MJO is tropical, is a variability in tropical thunderstorm activity over the equatorial parts of the world. And tropical thunderstorms are quite noisy. They're individual small scales that can be grouped together, lumped together in larger scales, but the real life signal is still quite noisy, just like the temperature field I showed you in the last slide. But I think it shows it very nicely how you can have space over time and this nice periodic variability with a time scale of about 40 to 50 days as the oscillation propagates around the equator. Back to some of the work by Madden-Julian. Their classic paper, I think, is one of the key figures in modern meteorology. The classic paper that they published in JAS 1972 has 8 different phases: F, G, H, A, B, C, D, E. I don't know why they didn't start with A, but they didn't. And they're showing along the x-axis is longitude: Africa, Indonesia, South America. So longitude is on the x-axis. The y-axis for each individual panel can be thought of as pressure or height. And they're showing the progression, the eastward progression of a thunderstorm anomaly. So here's the little schematic. It looks like a thunderstorm anomaly, or looks like a thunderstorm, and it's the location of the anomaly. The transition from phase to phase is about 5 days. So if you think 8 phases, 5 days per phase is about 40 days total. A couple of other interesting things show up, that there's usually within the oscillation, there's a rising or an ascending branch over part of the world, and then there's a descending branch that's coupled to it. The spacing is not always coherent, but they do move in phase around the planet. The thunderstorm activity vanishes essentially when it reaches the colder equatorial Pacific Ocean, which is not nearly as favorable for deep, robust convection. But the ascending branch is still present, and then the theory is, as this ascending branch returns back over the warmer waters, it would sort of kick off the oscillation again. That's a very rough explanation of something that's pretty complex, but that's generally the idea of the self-propagating method of the MGO. So this mechanism has been going on for a very long time, and is even going on today. And some of the questions that the community has unpacked recently have been like, okay, well, if you have heating that sits over a part of the world, and this is one of the classic papers from JAS from the 80s that examine this, these guys placed a heating anomaly over Indonesia, and then looked at the stream function response to the atmosphere. So these dashed and solid lines are anomalous stream functions. And these guys found that just by placing a heat source, an anomalous heat source here, the entire world responds. And there's a very nice wave train. Maybe you can see you have negative, positive, negative, positive, negative, positive, a very nice wavy response in the stream function to anomalous heating. And essentially this is what MGO does. This anomalous heating, as it moves around the equator, will produce poleward propagating waves that then mingle with the other waves that are already existing in the other parts of the world, and lead to some, in averaged sense, some anomalies. And these anomalies are what caught my attention in multiple parts of the world, and will eventually get to the point of all tornadoes. Some idea of quantifying Madden-Julian oscillation, or determining where it is and how strong it is. This work, the community has made many attempts to quantify. Matt Wheeler and Harry Hendon from Australia, Matt's from Australia, in 2004 put together a very nice metric that the community sort of rallied around. So probably, if you looked at their citation, you'd probably find 500 papers that have cited their index. So the community really has converged on this type of an index. And instead of using letters like Matt and Julian did in the 70s, and Matt and Harry use numbers. But this is the same idea, trying to identify where in the world is the heating source centered. And then secondly, what Matt and Julian didn't really do with their index, but these guys do, is how strong is the heating index? And that's the distance from the middle of that figure would be how strong the index is. So here's a picture of the last, I think this is the last month or so of MGO. So it started out centered over the West Pacific and Western Hemisphere, and in the last sort of 30 days has progressed, and currently, or as of yesterday, it was sitting over between the Indian Ocean and the Maritime Continent. And the yellow and darker green colors there are ensemble model predictions of where it might be into the future, with some statistical spread mapped over top of this. And this is taken from the NOAA CPC website. So this is an operational product that NOAA produces, is predicting where the MGO may be. The predictions are for a 2-week period, going from just a few days ago to about 2 weeks from now. And the idea of the predictability of MGO is really nice, because tornadoes by themselves are really unpredictable. All small scale features are really hard to predict at long time scales. However, the large scale features, planetary scale features, can be predictable at large time scale. And if we can make connections between large scale and small scale, then we can perhaps bridge this gap between the predictability of small scale features and future time to extend predictability to the future. Okay, so I mentioned before I got to the question of MJO and tornadoes, I wanted to show a few things that I and others have done on Madden-Julian oscillation. One of the parts of my dissertation at Oklahoma back in the mid-2000s was to examine MJO in tropical cyclones. And I think that's the community as well, that was the first thing that was examined, MJO in the tropics or the subtropics. Since it's an equatorial trapped phenomenon, it makes sense that its effects would be directly focused there. And my advisor and I published a paper in Monthly Weather Review in 2009 that showed that landfall points here, and this is North America and the Caribbean and Central America, landfall points were dependent quite strongly on phase of MJO. And we have some physical explanations of all steering currents and genesis of TCs as well. But more than genesis, this is mostly a result of the steering currents pushing the storms toward the U.S. or pushing them away from the U.S. and the Caribbean. You probably can't see, unfortunately, the quality is low, but this is a paper that just came out in Journal of Climate a few months ago for the Western Pacific. So that is there is Japan, so there's Japan there, Japan, and China, Philippines, etc. And the point is that for several of the other phases of the MJO, 1 and 2 and 7 and 8, there are lots of landfall points in that basin. And then for phases 3, 4, 5, and 6, not nearly as many landfall points, not nearly as many genesis points either. So for the Western Pacific, there's also an effect on, a stronger effect on genesis than I found there for the Atlantic Ocean. But the point is, yeah, MJO, the steering circulation around the world that changes as a response to this strong heat source centered over the equator modifies the landfall points of tropical cyclones. Another thing that's modified, this was introduction mentioned, I spent my postdoc year in South America, in Santiago, Chile. I got to take some students back with me. They really enjoyed their spring break there in Chile. We looked at Sarah and Tony are sitting in the picture. They actually are co-authors on my paper in Journal of Hydromet. We looked at the variability of rainfall in Chile by phase of Madden-Julian oscillation and found that, yes, indeed, that the circulation changes, global circulation changes, projected onto winter season rainfall for the country of Chile. And the rainfall in Chile is mostly from the center of the country in south. The north of Chile, the Atacama Desert, is very dry, hardly has any rainfall. So the anomalies up here might be spurious, but the anomalies in the south, for sure, we found very nice relationships. And not showing any of the relationships, we found very strong anomalies in the height field and the forcing for precipitation in central and south Chile is from traveling wave cyclones, traveling mid-latitude cyclones that come up from the South Pacific. And the response in the height field due to MJO, or composite anomalies from the height field, showed very strong agreement that the phases where there was a wet part of, for example, here in central and south Chile, phase 2, the precipitation anomalies above normal, there was a nice trough offshore of Chile. I also looked at air quality of the city of Santiago, Chile. So this is where I lived for a year of postdoc. The mountains, the Andes Mountains are smog covered, can't see them, but they're back there. Got to take some more students to see the smog of Chile. And then Kelsey is actually the lead author on this study of the ozone variability of several stations there in Santiago. And ozone is a summer pollutant, the surface ozone is a summer pollutant. It depends strongly on incoming solar radiation or insolation, which depends on cloud cover, which depends on circulation. So you see the idea of a cascading scale effect. You have large scale MJO projecting into synoptic scale variability, projecting into mesoscale variability, and out pops a pretty nice signal of ozone in the metropolitan Santiago area. All right, so that leads me to the bulk of what I want to talk about this afternoon is the Madden-Julian oscillation and severe weather. So I wanted to spend a bit of time on the schematic here. I've already introduced it, but just to remind ourselves, this is hypothesis that myself and my students have been looking at the last few years is we have tropical convection that's very much related to Madden-Julian oscillation, and then the response in the atmosphere of this tropical convection is wavy, and the waves propagate poleward and eastward for the most part in the atmosphere. And these waves, as they propagate away from the heat source, will eventually reach the middle of the United States. And what my students and I wanted to look at was, okay, if we know that MJO is getting to be predicted 2 or 3 weeks into the future, tornadoes are not predictable 2 or 3 weeks in the future, but if there's a relationship between MJO and tornadoes 2 or 3 weeks into the future, then we can connect the dots and at least speak about the likelihood or such of perhaps outbreaks or higher than normal likelihood of tornadoes or lower than normal likelihood of tornadoes. And so again, the idea is that the large planetary scale MJO projects onto synoptic scale waves, which projects onto mesoscale conditions like CAPE, helicity, other measures of vertical wind shear, which then will turn into supercell thunderstorms and tornadoes in the middle of the United States. So the first half of the study was spent looking at tornadoes. I'm also going to show preliminary results that another student and I are working on of hail, and talk a bit about some of the differences in the methodology. Tornadoes are very rare events. Hailstones or hail events are not quite as rare, so we could be a bit more spatial in our analysis of hail versus tornadoes. We're able to be very spatial. I'll talk a bit more about that in a second. All right, so another quick introduction to be a bit pedagogical in case those of you who are spending your PhDs coding microphysical parameterizations in a model, maybe you don't know what causes tornadoes. So I wanted to show some of the classic work from, this is an upper schematic here from Chuck Doswell and his monograph that basically tells the ingredients for a tornado outbreak, or the ingredients for tornadoes. You need a surface cyclone, you need an upper level jet around upper levels of the atmosphere. You need a low level jet from a different direction that's bringing up moisture. And you need some surface boundaries, either dry line or frontal systems, frontal boundaries, to trigger the deep convection. And if you have all those ingredients, then you can get thunderstorms that could produce tornadoes. I thought this was interesting. This showed up on my Facebook feed yesterday. I guess this guy, Art Hertz from Iowa State, put together a map showing the number of minutes by county, and this is an average number of minutes for the last 30 or so, 1994 to 2003, the last 20 years of tornado warnings. So here in Long Island, you guys are spending on average, can't see the numbers, but it's 5 or 6 minutes per year under a tornado warning. Probably one tornado warning every 3 years, it's 20 minutes long, and there's your average. Whereas if you're up by Denver, Colorado, in Weld County, or whatever the counties are, by Denver, Arapahoe County, Adams County, you're 180 minutes per year, so 3 hours per year. Somewhere in that county, Cherry County, Nebraska shows up as well. But interesting as well, down here in the southern part of the Gulf Coast, there's some counties that show up of tornado warning. So there's some blending of, this is not where tornadoes occur necessarily, but this is where the Weather Service has told the public to take shelter because of a possible tornado threat. So I thought it was interesting just to try to take Doswell's perhaps schematic for classic tornado genesis and then think, where might that occur? Where might the Weather Service have told the public that it's possibly occurring? And there's some spatial dimensions there. And again, there's a NOAA product, so the warnings are NOAA products. There are some human influences, but interesting nonetheless. Okay, so the study that looked at both MJO and tornadoes and MJO and hail used 2 primary data sets: the severe weather data set, which is maintained by currently Greg Carbon of the SBC, who's the warning coordination meteorologist there. The tornado data set and the severe data set contains reports from 1950 to 2013. However, the large majority of that data set is not really quality controlled, or doesn't have a lot of, there's concerns with the quality of the data set. If tornadoes weren't reported or didn't hit anything in 1963, they're probably not showing up in the data set. Whereas nowadays, we have the 88D Doppler radar, which is very, very good at detecting mid-level rotation, and the Weather Service offices are aggressive at going out and verifying tornadoes. So to perhaps mitigate some of those concerns, in our studies, we're only looking at the last 23 years, from 1990 to 2012. As well, for the tornado data set, we're going to transform the tornado reports into just a binary, yes or no. Did a tornado occur on this day or not? For the hail data set, we can do the same thing, but the binary will be gridded, so we can do a spatial analysis for hail. We use North American regional reanalysis, which is quite high resolution, one of the highest resolution products available. It's for 1979 to 2012, I believe, it's study. 30-kilometer resolution, and we have variables of geophysical height, cape. For hail, first, tornadoes will look at 0 to 3 kilometer shear, 0 to 6 kilometer shear, etc. I mentioned we'll do this exercises in binning. We'll look at the composites of tornadoes, composites of tornado frequency, composites of hail frequency by phase of MJO, as well as the amplitude of the MJO must be greater than 1. I didn't highlight that in the last figure, but if there's not a lot of tropical convection anywhere on the planet, then the amplitude of the MJO will be pretty small. We're not interested in days that have no tropical convection. If there's not really an MJO event, then we weren't interested in it. So we stratified by only those days where there are MJO events. And for the last 30 or so years, about 60% of the days are active and 40% are inactive. So we're looking at about 6 out of every 10 days for the months of April and May. Those are the 2 months with pretty high incidence of tornadoes and hail. So look at the months of April and May. We'll do some binning and some composite calculations of the NAR analysis data. And again, look at April and May separately, not together, because the mean frequency of both tornadoes and hail changes from April to May. All right, so here's the main result. I'll spend a bit of time on this figure to have this figure for April, and the very next slide is the one for May. All right, so what do we find? We found that, yes, there is a relationship between phase of Madden-Julian oscillation and frequency of tornado days. Frequency of tornado days for the middle of the country, from the Rocky Mountains to the Mississippi River, approximately that zone of the country. And not only is there a relationship between MJO and tornadoes, but the relationship is supported by cape and shear, which is a good thing. If there's a statistical relationship between something, the two parameters, there should be some physical reason behind it, and sure enough there was, which gave us some confidence. Myself and Victor Gensini from College of DuPage published this last year in GRL. So the 2 phases for April that we found to have above normal likelihood of tornadoes in the middle of the country were phase 6 and phase 8. Phase 6 and 8 there with the solid blue arrows. And the 3 phases with below normal tornado likelihoods we found were to be phase 3, 4, and 7. 3, 4, and 7. And for the phases with above normal likelihood of tornadoes, phases 6 and 8, we then looked at cape, 0 to 6 kilometer bulk wind difference or bulk wind shear. We also looked at 0 to 3 kilometer helicity and 500 millibar geometrical height. I'm just showing you the product of cape times shear. So if the cape is 0, that then wipes out whatever the shear is available. So you see for phase 6, maybe you guys can see this, there's yellows and reds. And yellows and reds, sure enough, are positive anomalies for those 2 variables, cape and shear. So in phase 6, when there's higher than normal likelihood of tornadoes in April, sure enough, there's also more cape and more shear than normal. For phase 8, for much of the central part of the country, there's an above normal anomaly. There is a below normal anomaly that shows up there in West Texas and Western Oklahoma. And I'll talk a bit more about that in the hail data set. We were able to do some stratification by space, not just the whole middle of the country and take it as one binary yes or no. For the below normal phases, look, for example, phase 3 shows up pretty nicely, as well phase 4. Those blue colors are below normal anomalies of cape and shear. So again, the hypothesis is large-scale tropical convection projects onto wave train, which causes less cape during phases 3 and 4 and more cape during phases 6 and 7, which then leads to slightly higher or lower, respectively, anomalies of tornadoes. Same thing for the month of May, but the phases were different because the world is different in the month of May, so tropical convection causes different waves. The waves move different speeds. So some of the phases are similar, but some are different. For example, the highest tornado frequencies occurred in phase 5, 8, and 1. and the below normal occurred in phase 2 and 3. And here, perhaps 5 is the best example. We have this really strong positive anomaly there in the middle of the country, some below normals in the tops and bottom up in the Dakotas and down the Texas Gulf Coast, but a strong positive anomaly in the middle of the country that sure enough agrees well with the above normal incidence, of above normal frequency of at least one tornado in the middle of the country. But May has had maybe a mixed signal. Phase 1 as well, not as mixed, but then if you look at 3, for example, we have a below normal frequency of tornadoes. We still have a really high positive number over Mississippi and Arkansas and Louisiana, Tennessee. Again, probably arguing for some regional separation, that I and my colleague took the entire middle of the country and treated it all as one. And likely phase 3 should be treated as more than just one place. That the below normal frequency probably is the middle of the country, the plains, and maybe there is an above normal signal in the eastern part of the country. Didn't test that for tornadoes. The challenge is tornadoes are a very rare event, and if you start limiting your data set, statistical significance becomes a problem. You have very few numbers to really test by. But this was the nice result. By the way, I'll go back to April. Phase 6 was an above normal phase. Phase 6, according to the GFS, is coming in about a week. So you guys can test our theory. If we have tornadoes in a week, and we don't have them in 3 days, we have them in 7 days, then maybe the signal does show up. Same thing, phase 8 is predicted to come in about 10 days from now or 11 days from now. So we'll see if either of these work out for the month of April. Okay, so then the last piece of the work that I'm actually doing right now, is to broaden from the tornado data set, which treats the entire country as one grid. Now we've gridded hail into lots of little tiny boxes. So instead of one box, we have hundreds of boxes. And because hail is much more a common occurrence. The mean frequency of hail for Oklahoma and Texas is 1 out of every 10 days in April has hail in these boxes. In the month of May, there's lots of parts of the country that have hail at least 1 out of every 10 days, 3 or 4 days in the month. Even up here in New York, you guys get hail every 1 day a month, maybe in the month of May, out here in Long Island. Okay, so these are composite anomalies of hail for the month of April. And the most important thing I take away from this is the spatial variability. There's not, for example, phase 1, there's a dipole. The northern part of the country has below normal hail anomalies, but the southern part has higher than normal hail anomalies, which would maybe argue for some very nice spatial separations. Other phases may not have such strong separation, like phase 5, for example, seems to be above normal for most of the country. Phase 7 seems to be below normal for most of the country. When I flip to the month of May, similar patterns show up. The phases change as the substrate that the planet is. The MJO projects differently onto that in the month of May than it does in April, so the phase numbers change a bit. But still some of the same sort. For example, in phase 5, there may be above normal hail frequency in the southeast and middle Atlantic, whereas there's below normal hail in Texas and Oklahoma. Argues again for some perhaps spatial separation. Again, mentioned this is more preliminary, just presented this at the AMS annual meeting back in Atlanta 2 months ago, so my student and I are still working through it. But we took those hail anomalies and matched them with Cape anomalies and found some pretty good agreement. Like I'll point out, for example, back to phase 1. You probably can't see, but this is a blue line, and this is a red line, and then you have a blue shading and a yellow shading, so showing that the below normal hail anomalies occur with below normal Cape anomalies, and the above normal hail anomalies occur with above normal Cape anomalies. There's some interesting conflicts in that. I think phase 7 shows up. There's a below normal anomaly here, kind of surrounded by yellow shading, indicating Cape is above normal, but maybe the hail is not above normal. The month of May had similar results, with matches in some places, mismatches in other places. That led us to then turn to upper level height. So these shadings now are 500 millibar geopotential height anomalies by phase of MJO, co-located with hail anomalies by phase of MJO. This is for the month of April. Generally, as the result we were encouraged by, generally the presence of a low height anomaly or a trough anomaly are co-located with above normal hail anomalies. So the presence of a trough generally leads to along and to the east of that trough anomaly, the low height anomaly, leads to positive hail anomalies. And we were encouraged by that result. But it doesn't always work out like that. We have not yet tested vertical wind shear. That's where we're on this week or next week going to do that, on the cusp of testing that, to perhaps get a bit more clarity for the hail anomaly. Okay, so to conclude about tornadoes again, there is a relationship between phase of Madden-Julian oscillation and likelihood of a tornado day. That relationship is different for the months of April and May, with some similarity. Phase 8, for example, shows in both months. These anomalies were strongly supported by anomalies in the ingredients for tornadoes, such as instability, vertical wind shear. There is regional variability that has not yet been explored. Part of the hail study is looking at this regional variability in a bit more detail. So for the conclusions for hail, again, there seems to be a signal between phase of MJO and also for hail frequency. And that signal also seems to agree with both dynamical vertical wind shear forcing as well as thermodynamical forcing. But we're still in a preliminary stage here. We're going to go back and refine this a bit more and do a bit more regional testing there. And also to match it with the tornado signal, to see if there's any good agreement between certain phases that seem to favor. If a phase favors tornadoes, it probably should favor hail as well. All right, last piece. Another colleague and I may recognize the schematic a few slides ago. Just took the waves and moved them to the Arctic and looked at sea ice concentration. So I just wanted to show this very briefly. Some of you may do work in modeling of the Arctic or some other. The Navy, who employs me, is very, very interested in the Arctic, so they were very happy that we're studying the Arctic. As sea ice is vanishing, there's likely to be a lot of activity in the Arctic, especially during the warm season. So the same question, but move it to a different variable from severe convective storms going up to sea ice concentration now, and ask the same question: does phase of MJO affect ice? And we only focused on the margin seasons. We weren't interested in the minimum or the maximum. We're interested in where ice is changing, when ice is melting or ice is freezing up. So we focused on those months. Just really briefly, these are composites for seasonal geopotential height at 500 millibars. And the point I want you to take away from this is there's reds and blues in every panel. So there's a wavy response to MJO for both winter and summer. Summer response is more muted than the winter response is, but for every phase of MJO, there's an atmospheric response to MJO, and that atmospheric response, our hypothesis, is going to project all the way down to concentration of sea ice on the surface. And just as one quick thing, the full paper is in Climate Dynamics, just out in January. But for phase 4, we found off the east coast of Greenland a very nice signal of below normal ice concentration anomalies for phase 4 that was supported by warm temperature anomalies and wind anomalies and blowing the ice away from the coast. And then for phase 7, we found the opposite. We found a positive ice change anomaly. So there's more ice freezing during phase 7, supported by colder temperatures and wind blowing the ice toward the coast. And this was a very nice result that we're still exploring more as well, to perhaps extend from just ice in the Arctic to perhaps snow cover over the Pan-Arctic region. Okay, so last thing I'll finish here, just to give some idea of where this really is actually fairly preliminary work, but where this might go into the future. The idea of transforming these statistical relationships into an actual predictive model. And I think that'd be really interesting, and the community would really appreciate and find a lot of value in that. That's also the hardest part. It's easy to make composite anomalies and show these results. Much more challenging to stick it into an actual model as well. It's risky, because once you start predicting things, then you can be right and wrong. Whereas if you don't ever predict anything, then you're never wrong. So that's where we're headed with this. We want to look both for severe convective storms and also for ice and snow in the polar regions. All right, so that's concluding here.
questions, right?
Sure.
So, let us see any questions. Thomas,
Yeah, two questions. In the beginning, when we are looking at the tornadoes, and you picked phase 3 and 4 as the low end. But when you look at the numbers statistically, the error bars were almost the same as 5. What made you not include 5?
So if you're asking why I said, oh, phase 3 and 4 are low and phase 5 maybe not as low.
The same.
It was a qualitative response. If phase 5 is below normal, then phase 5 is below normal. Then maybe 3 and 4, if I remember correctly, were statistically significantly below normal, and 5 was not. If I remember correctly, I have to go back and look. But yes, so 5 maybe was below normal, but not statistically significantly below normal.
Okay, my second question was on when you look at the season, especially in terms of temperature, if you are here, say in April, and you go down to DC, you can notice that it's already changing. So that phase, the phase difference in terms of temperature evolution, how does it factor into how you pin your occurrence? Could the phase difference matter because you're putting things into different months, but the May of Long Island could be the April of DC.
Yes, I agree, and I think that argues for why we separated April and May to begin with. But then, I think perhaps more importantly, for tornadoes, the ingredients for tornadoes are the same. So you have to have cape, you have to have shear, and if you have a tornado in Long Island in April, it's a very rare event, but it means you had cape and shear. So the composite of that would still show, well, not one event, it would still show it. But you're right, you have to split. April and May are separate.
So that's what
For
Sarah,
latitudinal variability.
Sarah, you have a question?
Great talk, very interesting results. Do you think there'd be any utility in separating MJO by the strength of the phase? I mean, you have a minimum threshold, but what about getting into
Sure, that's a fantastic question. Short answer is that would be a great question. Yeah, I think that would be something of interest. I don't know if, for example, in the modeling studies, I don't know if the folks in the 1980s, if they put their heat source and they vary the intensity of the heat source and saw, oh, the streamlines got more intense or less intense. I don't know. I would think yes, but it's a speculation. I think yes, it would be an important, interesting question to examine.
Just one second. Ping, do you have a question?
Yes, I looked at the variability index very carefully while using paper present plan dynamics. Looking at that, the variability index based upon the first 2 modes. The first 2 modes is very strong in convection in the eastern hemisphere, which is probably less interesting than analysis.
Except for teleconnections. That's
Right.
why it's not a direct response, a teleconnection response.
Yes, okay. Phase 8 actually corresponds to the ITPA mostly in the western hemisphere.
Which, by the way,
yes,
is
it's
a
broad.
huge region.
It's broad.
Yes,
Which means
from Dateline all the way to Africa.
Yes, more contribution comes from the circulation rather than convection. So my comment or question here would be that in my analysis, I looked at the modes 3 to 10. Those extra modes will actually compensate most of the MGO convections near the daylines of the Western Pacific, and perhaps could be more relevant to the activities in our area, for perhaps for the tornado or even some of the events.
That's true.
So yeah, in that sense, probably it's worth to look at those modes as well.
Very fair point.
I just one second.
I have 2 questions. So you used the data from 1990 to 2012, right?
Yes.
So it's 23 years
Yes.
for April.
Yes.
So in April, for how many strong like RMM rather than 1? How many MJO cases do you use? In the
Great question. Certainly, I think your point is the data set is limited. Yes.
So maybe like half of the MJOs in April, then you have 12 cases, like 10 to 12 MJ, strong MJO in your for your composite in April.
Sure. Yes.
Right?
Yes.
And then you divide it by phase, then it's 1 or 2 cases.
true. However, the phase, as you know, the MJO can sit in the phase for several days, and we count all of those.
Okay.
Yeah. So it's not just, oh, one phase, that's it, only count once. No. So the response will build, and maybe sort of her question about the amplitude can be refined with duration of MJO in a certain phase.
Sorry, yeah, I do have another question.
Yes. So in April, the NGO is magnitude is not that great, but in May, I think the NGO start the northward propagation to the Asian monsoon regions. And so how, for May case, I think the samples will be even more decreased in NGO cases.
In terms of the number of active MJOs?
Yes.
Possible. Possible. I don't know. Yeah, it's possible that there are fewer cases. Maybe, but May is still early for that, for the 8 months.
Edward, please.
I'm just wondering, you sort of treat the wave train as sort of instantaneous response because,
Yeah, there's a lag.
But in reality, the wave battery takes time to build and propagate.
Exactly.
And it would seem that depending on this propagation speed of the MJO, the wave train would be different. And so some of the signal that's not seen maybe because you're mixing up the different.
Very valid one. Yes, I agree that if there's tropical convection over Indonesia, for example, how long does the response take to arrive in USA? Yeah. Some days. It won't happen. Yes. Great point.
Oh, yes, Mingwa, yeah, Mingwa.
Yeah, I assume that the relation between tornadoes and MGO hold true. And how about how well MGO is predicted in the model?
Another good question. The predictability has improved every year. And I was just talking with Professor Kim a few minutes ago before the talk about how the predictability is maybe out to now 3 weeks with some skill in both ECWF and GFS, maybe 2.5 weeks, 3 weeks. Yes, so there's skill in prediction of phase and amplitude of MJO.
So have you thought about how you're going to make this prediction, given the title of your talk?
Not yet.
Not yet.
I have some ideas, but as I mentioned, that's the best result. The best use of the result is to formulate the model. It's also the hardest thing.
So there needs some kind of, I use the word, statistical model that allow one to use some kind of generic type idea to swing whatever the parameters you are interested.
Certainly, some sort of regressive.
Okay, yes,
I was curious how this information can be used. Like, for example, you tell the population it's going to be increased probability of tornadoes in 2 weeks. What's it going to be about?
It's hard to get them to go in the basement and tell them we get a tornado in your house in 5 minutes. So yes, the use is not for the general public. It will be for science or some. I think the awareness of the community, for example, the current operational products from NOAA go 8 days into the future. The same question could be asked for why does NOAA produce an 8-day forecast for convective likelihood, for awareness of the emergency management community, for awareness of the science community, not for the general public. Yeah, I agree. They don't take response even with the short-term fuse. They're not going to respond 10 days into the future.
Okay, so no more questions. So let us thank
Thank you all.
Yeah, that's about.
Okay.